recording. Okay, so let's calculate the first moment of the area, but for this section. Okay, this is a rectangular section, right? But it's not the same as we had before. Okay, similarly, it's we have to be aware that this is X in this direction, that's the beam direction. Okay, so this is X, in the vertical direction is Y, and in this direction is Z. Okay, now, in these cases, you see that if we define this sector, it's going to be different if we make a cut down here. Okay, so what we can do in these cases is to obtain expressions for different areas, okay, of the same section. So in cases where you have combined shears section, we can do it by regions or zones. Okay, so what I'm saying is that in this case, we're going to do an analysis. This could be the deck of the simple barge. And then we're going to do an analysis when we make a cut on the side of the barge. Okay, so right now, this is the sector. This is the sector that I'm doing. Now, in this case, okay, since the cut is here, and we will go up to this point. Right now, I cannot explain it to you. I'll do it tomorrow or Tuesday. But here, since we have a symmetry axis, tau, in this case, going to be Zx is 0. So if I make a cut here, in that case, the cut will be defined at the position Y. If I make a cut here in this direction, then it can be identified with the direction Z. So in general, it's better to start using this like an S. It's a position of the cut. So it could be Z or it could be Y according to the geometry of the section, okay? So if we had a very simple geometry like the previous example, we could explain Q as function of Y. In this case, if we make a cut here, we will need Y. If we make a cut here, we need S. So the S variable means it's a more general position, which is employed to specify where you are doing the cut. Okay? So this is the position of the cut. And we're going to integrate from here, from S until here. Why until here? Because as we said before, we know, I have not explained it to you, I'll do it next session. This is equal to 0. Tau is equal to 0. So we go from here to here. Okay? Now, this is little b, and this is large B. In this case, I'm using little b for half of the width of the section. Okay? So we are going to calculate Q as function of S. This is the S that we're going to be using. So here, it's going to be S of the sector, and then it's multiplied by Y average. Okay, people, tell me, what's going to be AS? The area of the sector, this crossed area right here. somebody in particular.
H over
people?
2 minus T.
No, first just A, so A. So the area, that's all.
Large B times T.
So it's going to be B.
B over
little b
minus S.
exactly. B little b. Oh man, damn it. Little b minus S. So this is going to be the distance from here to here. And then we'll multiply by the thickness. In this case, I'm going to use only one single thickness for the whole section. In general, remember, in the ship, usually the thickness at the deck, at the side, and at the bottom are different. Okay, but in this case, no. We are just considering that it's a very simple barge. Okay, now, how about the the Y average? How much is the Y average? Mr. Kimi, tell me, Y average. Position of the centroid. Mr. Kimi, please. Let me waste time. Come on, we don't have too much time. Mr. Hidrobo,
Present.
how much is going to be Y average?
Yeah. H over 2.
Yes,
Minus,
H over 2. Now, you can say that H over 2 minus T over 2. The problem with this is very small. Okay, so in some cases, you can have a section which is very small. So H is, for example, in our lab, you're going to do this in our lab. And it's possible that this H is, I mean, it's not that large. Maybe, for example, it's 10 centimeters. And the thickness could be, for example, 2 millimeters. So this is going to be a very small percentage of that. But it is possible that you have sections in which these two dimensions are not that different. In that case, this is the exact one. Okay, so we are going to say, in this case, we're going to accept this is enough. So we can say immediately that Q of S is equal to this one here, B minus S T, and times H over 2. In these cases, okay, it is possible, and some people like to make define the sector simultaneously. Start it here and consider the whole thing here. So we have to be careful. So in this case, we are saying that S goes from here until here. So we have to say that in this case, S values between 0 and B little b. Okay? So let's draw. Okay, so this is the upper part of this. In the vertical direction, this is the Q of S. And in this direction, I'm going to include S. Yeah. Okay. When we are here, but in this position, S is 0, right? If S is 0, we have the largest value. If we are here, how much is S, people? How much is S here?
B.
How much is
B.
S?
Small b.
Here to there, S is little b. So we put little b here, that's going to be 0. And you see that it is linear relationship. So we're going to have from a certain value and linearly varying like this.
Excuse me, doctor, I have a question. Why T over 2? Why you consider
Why
T over
what?
2? Why you consider T over 2 and Y minus T over 2? Because I see the distance, the distance between neutral axis to the center is H over 2. Why you consider T over 2?
Okay,
Just tell
if
me.
you make a zoom here, this is what you have. This is the thickness. This is H over 2, and this is T. So that's your rectangular sector, and this is the position of the centroid. Sorry. This is the position of the centroid. So you measure from here until here. So it's going to be up to here, and then you subtract half of the thickness. That gives you this distance. And what I'm saying is that in general, this number is small in general. There could be some changes, some cases where you have to consider this dimension. And since this is very small, we can say that this is simpler to write it like this. So it's like having this very thin compared to this height. I don't know if I answered your concern, your question.
Yes, doctor. Thank you.
So if we make an analysis in the other side, okay, we could say, okay, let's change color. We make a cut in here, and we can consider this as our sector. And again, you see that we start here and we can go up to here because in here, the stress is 0. In this case, we can do the same analysis, and then we could have something like, please remember, the area is always positive. People, there are some movies that tell you, yeah, there is a anti-area or something like that. No, this is the real world. In the real world, the area is always positive. Okay, now the other parameter, y average, that could be positive or negative. Yes, but the area is always positive. Okay, so be careful with the signs because this is very delicate matter in this part. Okay, now, so we have calculated the first moment if we make cuts on the deck of this barge. Now, let's consider a cut on the side here. Now we have a cut side. I don't like that color. Let me try to see if I can recuperate. See this cut at the side. So we'll make a cut here. Now, the distance from here to here is y. Now, and we integrate from here all the way up to here. So all of this is the sector. Now, this sector is composed of this part, this vertical rectangle, and this and the deck, half of the deck. So we can say as that. In this case, we have Q is going to be Q at the side plus Q at the deck. Because we have to integrate from here all the way up to here, because here the stress tau Zx is 0. If we go from here until here, you're going to say that in this cut, you don't know the stress. In this cut, you don't know the stress. So you have two unknowns for only one equation. That's not going to be enough to calculate it.
Excuse
Okay,
me.
that's why we need to go from one cut until a point where we know the value of the stress, and that's 0. Okay, so let's go up. What's going to be the first moment of the deck? So we have the full rectangle. So the area, Miss Santos, do you have any question? Miss Santos, do you have any question?
Yeah, I can get at you almost because I couldn't see your mouse where you are pointing.
Can you see it now?
No,
What about other people? Can you see what I'm writing here?
I have the same problem, doctor.
yes, where you are writing, yes, but when you are pointing the,
I have the same problem. I have the same problem. I don't know why, but I don't see, it's very difficult for me to see the pointer. Okay. Okay. If you have any doubt, just ask me, because that's all what I can do. Okay, let's go on. So the area of the deck is going to be the area of the rectangle. That's easy, right? Because that's B times the thickness. This is rectangle here. And the distance to the centroid here is approximately equal to h/2. So here we are neglecting the thickness of the deck. We consider that this very small compared to this large magnitude. Okay, so h/2 minus t/2 is approximately equal to h/2. Now this is a constant. Okay. Now comes the most interesting part, Q of the site. Okay, and this depends on y, because the point where I make the cut, which I define as y, changes. So you can make a cut down here, or you can make it very up to here. So this is a problem that we already solved. Let me go back. Okay, so this is the same. You see, it's a vertical rectangle. You have the cut here, and you will go up to the top of the rectangle, which is h/2. And the result was this. So we're going to take this expression, and we're going to replace it. Our problem here. So it's going to be this here. This is very small width, is the thickness over 2. And then we have h/2 squared minus y squared. And finally, we have to add them up. So if we make a cut here, we're going to have the combination of these two terms. If we make a cut here, at this point, you see that we are on the neutral axis. This is going to be 0. With this negative, that means that on y equal to 0 on the neutral axis, the combination is going to be the largest. So we're going to say that Q as function of y is going to be this, which is constant, BT h/2 plus t/2 h/2 squared minus y squared. And you see that there is a negative sign here. So when you reduce this, you have a higher value of Q. So at y equal to 0, Q is max. And that's the same result as we had before. So every time we do this type of analysis, we are interested in the region around the neutral axis, because in that area, the Q is going to be very large, and the shear stress, which depends on this Q, is going to also be very large. Okay? Any questions about these, people?
yes, doctor. Where do you start to the Q of side? At the top, since the top, or down to the top? Without
Well,
the thickness of the top.
The thing is this, see, this is very small. We're saying that this thickness is very small. So it's like having a line. Okay, so it's having a line. So the thickness of this plating is very small. So there is no distances. So you go up to here, and then you go to the right. If you consider the differences, then the analysis will be much more complex. Okay, so right now we consider that the thickness is very small. So there's no difference. Okay. Now let me summarize. Oh man, I need one more. Let me reproduce this. Shoot. Try to see. Can you see my screen, people?
Yes, doctor.
So right now we have two expressions, one for this side and one for this one here. So this is what we do usually. Okay. We draw like this, and on each side we set up an axis. So in this direction, in the vertical direction, I'm going to write Q. And in this direction, I'm going to write Q of Y. Similarly done here. Now, in the top, we set that the variation is going to be linear. So it starts here. Oh, shit. What a line, man. But this is on a straight line, leave it or not. Okay. Similarly for this side, this is straight. Okay. Now, let me go back here. If I evaluate on this side, this is the expression that I need to apply. But if I evaluate it here in this point, what's going to be Y? What's going to be the value of Y at this point? The value is going to be H over 2. So if this is H over 2, the second term is going to be 0. And this is the value when we evaluated, let me go back, when we evaluated here, because in this point, S is equal to 0. So in this point here, the expression will give us BTH over 2. So this value here is going to be BTH over 2. And now, if we plot on this side, okay, on this point, this is going to be H over 2, that's going to be 0, and we're going to have Y. Then, when we go down, Y is going to decrease. If this decreases, we have a negative sign, then Q is going to increase. And it's like drawing an arc of a circle. So we recuperate this value up here. So this value is the same as here. And now we go like this. Okay. If we draw in here, we're going to have the same as this one here, but well, it's the same, sorry, it's the same. So to help us, we draw an arc. We go like this. We go like this. Again, here we draw an arc. So we have the same value here and here. An arc. And this value will be the same as here. So that's going to be, let's draw with different color, the section, the original section. Let's call it in green. So the original section is going to be this one here. This is a section, small thickness, as a section, small thickness. Oh, shoot. There, and you see that's the variation of the Q. That's the first moment of the sector measuring from the neutral axis. Question, people? Questions? Questions? No questions?
I have a question, doctor.
Yeah, go on, please.
At the top of the plot, you're only considering the Q of S, right? I mean, it's just the
Yeah.
deck, the part of the deck.
No. At the top, yes. At the bottom, no. We're going to say that a little bit different. Yeah, but if I make a cut here, let's consider a cut here. Let's change color just to be sure that, okay, let's make a cut here. So in this case, we have to consider all of this, and all of this. And you go on all the way. So up here is going to be B T H over 2. We integrate this. Let me go back. So in this case, we are talking about this expression. So this part here. In this case, this Y, I'm evaluating in this point here, is going to be minus H over 2, but it is squared. So all this term will be 0. Okay. So from the side, if we evaluate Q at minus H over 2, it's going to be 0. It's on the side. And then here, this is going to be, I'm sorry, this is going to be, then I got confused. The S is measured from here. So this area is going to be what? It's going to be S times T. And the distance is going to be minus H over 2. So you add this plus 0 plus that, and you will get this line here. I don't know who asked the question, but did I answer your concern?
Yes, doctor.
Okay, so in these cases, we will go further on this topic, but it's better if we consider another integration, okay? Because we know that if we integrate over the whole half section, the integration has to give us 0, okay? Because remember, let me go back. Something I explained before, okay? The integration of the whole, of the stresses on the whole section has to give us 0. okay? So when we integrate all of these, okay, then the answer should be 0. So when we evaluate this case, we integrate all of this, the left section from here, up to here. We make it very close here. All of this integration has to be 0. So if this is true, instead of integrating all of this area, which is very large, what we could do is we could integrate the complement, and it's going to be much easier. But we have to be careful with the sign. Okay, but we will do that not today because we're just started with this topic. Okay? Did I answer your concern, people? Is there any other question, people? Is there any other question? No? Okay. So that's the first part of the session. Now, let's go to the second part. Now, I said that we're going to be reviewing what you did in the homework. Is there any questions about the homework, people? Any questions about the homework?
Doctor, I had a little confused when you
Yeah.
make the strains, the difference of the bottom minus the difference of the top, the top minus bottom. So why do you do that? Because maybe I think that you did it for make average, but the average produce a negative moment. But if I do a strain top minus a strain bottom, I have a positive sign.
Let me try to, okay, let me open a fresh. Yeah. You see my screen?
Yes, doctor.
Yes, doctor.
You see my screen, people?
Yes.
Yes.
If I can draw something in. Hopefully, yeah, I can draw it. Now, okay, let's go. I have my beam, positive bending moment. This is
Doctor.
X. Yeah,
Doctor, I can see that you are doing.
and what's
I see
wrong
the
today?
screen, but okay.
What's wrong with this? Let's see. See now?
Yes, doctor.
Oh, this is the situation. Okay, now, according to this, we have a certain value of strain up here. Simply say this is a strain that results from this application. Now here, we have a certain value of y. So let's call it at the top. So sigma x at the top is going to be equal to minus the bending moment and go on. Y at the top divided by I sub c. Similarly, we can say that this is going to be equal to that, and we divide it by E. At the bottom, it's going to be minus mz y at the bottom over E I sub c. So what I'm saying is that you measure the value at the top, subtract with the value of the bottom, and go on. And the thing is that y at the bottom is equal to minus y at the top. And then you relate these two expressions. And you can say that minus mz y at the top over ei sub c, we are subtracting, okay, minus mz over y at the bottom, ei sub c, and go on. Now, this one here is this one here, which is minus. So we have 1, 2, and 3 minuses. So we're going to have minus mz twice y at the top over ei sub c. And this is what you try to obtain. So this is just no assumption, just at the top and the bottom. If you want to do the other thing, at the bottom minus at the top, you're going to go the same thing, except by the sign. That's all. Miss Santos?
Yeah, because I thought that it was an average because at the top.
If you get an average, the average will be 0. Because at the top and at the bottom, you have the same value of the string, but different sign. So the average is going to be give you 0.
In the graph, you have at the top is to 0. It's like 0, and the bottom is down. So for this,
so you can get a difference. I mean, the thing is this. Okay, the problem is this. Okay. I now understand your concern. The problem is this. Let me change. I can find it. Here it is. Can you see the document, the PDF of the homework?
yes,
Yes, doctor.
Okay. So yeah. Okay. So here, oh man, let's try to see if I can draw here. I cannot draw. I cannot draw. If I can put it here. Okay, now let's see if I can. For some reason I cannot write in here. Okay, I'm just trying to explain it to you with this.
Doctor, you are not sharing the homework.
Oh, shoot. See it now?
Yes, doctor.
Okay. Let's consider, for example, one of the values, the curve with the black one. Okay. So this value here, you have to read it on the scale. That's the value that we had when the strain gauge was at the top in gauge number 2. Then you rotate 90 degrees, you're down here. And then when you rotate 180, it is in the lower position, and you have this value. So what you have to do is subtract this value minus this one here. The problem is that if we want to do exactly as in the theory, we would need to start or set up a certain situation where the strain is absolutely equal to 0. And the problem is that we cannot find that situation. So what we can do is just get the difference, okay? That's why we started at the top and we tried to set it equal to 0. And as our point of reference, we went on and measured the strain at the other position when it was 180. And it's just the difference between those two. Miss Santos?
So that difference is equal to the difference that I have to do
Exactly.
in theoretical case.
Exactly. Because when we started the experiment, these values, okay, were supposed to be the values of the strain when you have deformation. But the problem is that we didn't know those values. So we just started with any value that was given the measurements. But we know that the difference, okay, in the other document that I show you, we calculated the difference between situation when you were in the top minus the strain when you were at the bottom. So these values here are the results, are the measurements when you have the strain at the top. And these are the results that you obtain when the strain gauge were at the bottom. So you just get the difference, and that's all. Ms. Santos?
Yes, so is that why?
Yeah, we have to be very careful with the signs, okay? We're very careful with the signs because in these cases, for example, at the top and at the minus and at the bottom, the difference is positive. So with the same sign, you have to go on and include it in the expression that I just presented. So in this case, the difference is going to be positive. Yes. So the bending moment should be what? Should be whatever. But you have to be careful with the signs. That's my
The
message.
moment should be negative.
Yeah, could be, but you better check. Make sense? Yeah, when you have a negative bending moment, at the top you got tension, and at the bottom you have compression, and that's what we're seeing here. In the case of the first gauge, okay, the first gauge, okay, that's a very delicate one because this gauge is located well to the left, okay, so probably the values were very small, okay, and since the value was very small, these readings were probably we cannot trust them, okay, so we cannot simply compare because you're seeing that we cannot any adequate, any decent result from here, right? So you could take this value minus that one, or you can take the average of this, and that. But yeah, you can see that there is some tendency, so there's no steady. So we just neglect it, unfortunately. So we can compare only the bending moment in 2 points, not in 3.
And in that question, you say that to estimate the reactions. So
yeah,
with that position of the moment at the strengths, we have to build a function or just to put the reaction of theory.
the theory. It doesn't, what is it? Okay, yeah. the thing is this, okay? Let's suppose that, see, right now, somebody called me from the industry saying that they have a big problem with a large ship, okay? It looks like they grounded, so the aft part of the ship structure probably has some deformation, probably. So the classification society, the surveyor, is asking them, okay, they have made repairings and they have do a new alignment, but they have problems. So the classification society, the surveyor, is asking them to measure somehow the reactions on the supports. And I'm just giving you a homework, something like that. Let's suppose that we are able to measure the strains. With the measure of the strains, you get the bending moment. And with the bending moment from the original, from the experiments, why don't you calculate the reactions? And you can compare the values from the analytical results compared with the values of the reactions using this experiment. Yeah, so it's kind of a simple, very simple way to obtain a reaction in these cases. Okay.
Thank you, teacher. Doctor.
Any other question, people?
I have a question, doctor.
Yeah, go on. Please try to speak louder because I can.
Okay.
It's difficult for me to hear you.
For this exercise, we have to consider the weight of the shaft.
I'm sorry,
right?
I'm not listening to you. Would you please get closer to the microphone?
Can you hear me now?
Yeah, better. Go on.
Yeah. In this exercise, we have to consider the weight of the shaft, right?
The what?
The weight of the shaft.
Yeah, you have to include it.
And what is the material of the shaft?
The material
Is it
is
the steel? Okay.
Steel, yes. It doesn't say it here. Man, I'm sorry. That's an error from the assistants because they have to pick those errors and make me, yeah, it's a steel shaft.
Doctor, and in the exercise of the inertia, can we use the Morse circle for deduce?
People, see you tomorrow, right? Bye-bye now.
Bye.
By the